Section 13.4, which is about the which is the change of variables into polar coordinates. Okay, polar coordinates, which means we're going to do the double integral from by using the polar coordinates. All right, so our objective here is, first of all, express the region of interest, okay, region of interest in polar coordinates. Secondly, we want to evaluate and write the double integrals in polar coordinates. And thirdly, find an area of polar regions. Okay, so everything will be in polar coordinates. So very quickly, let us first of all recall polar coordinates. Polar coordinates is another system of coordinates compared to the Cartesian coordinates that we are pretty familiar with. Okay. Polar coordinates uses two coordinates. One is r, one is theta. Okay, and they can be related to Cartesian coordinates x and y. In general, I think we've talked about that in class before, right? So here, if this is x, o, y, then there is a point here. Then we can find the radius. This is r, and this will be the angle theta. Okay. So if I have a point right here, which is x, y, here would be x, here would be y. Okay. Therefore, x would just be r times cosine theta, and y would just be r times sine theta, right? R sine theta. And then for x squared and y squared, if you find the sum of their squares, it's going to be r squared, which is easy to see by using this right triangle here. X squared plus y squared would be the square of the hypotenuse. For this angle theta, its tangent value is going to be y, here is y, over x, right? So that's very quickly the review of polar coordinates, the transition between polar coordinates and the traditional Cartesian coordinates that we're familiar with. So the next topic is about double integral. Okay, double integral in polar coordinates. We have the intro problem as you guys see here. Okay, so take a look at this graph. Can you sort of see what's in front of you, and can you see a solid in front of you, and then take a look at its region of integration? Suppose we're looking for its volume. Okay.
Mm-hmm.
All right, so apparently there are two surfaces, right? This is the top surface, and then the bottom surface is like a bowl, right? So we have a bowl in the bottom, and we have a cover on top. In between, we have the solid here. You guys see that, right?
Yes.
So apparently you can try to calculate the volume of the solid in between these two surfaces. We know from our idea last time, volume will be double integral of, if there are two functions, right? Two functions. So function on top, which is going to be 2 minus root of x squared minus y squared plus y squared. The function on top minus the function in the bottom, right? Bottom, which is x squared plus y squared. And dA over the region R of integration. That's how you set up the double integration, right?
Mm-hmm.
Now the question here is, this time if you look at this integration of this region R, okay, let me simply project this region R on the xy coordinates, xy plane. This region R is basically a circle of radius 1, right? So here's 1, -1, and here. So this is our region R for integration. Now the question is how to express this region R, right?
Mm-hmm.
So the region R, as we said last time, if you use Cartesian coordinates, then you can do either x simple or y simple, depending on the shape of the graph of region R, right? Now it's easy to see that the shape of region R here is a pretty symmetric shape. Okay, symmetric shape. So whether you do x simple or y simple shouldn't matter that much because due to its symmetry, right? Due to its symmetry. Let's see how we can actually here. Suppose I change the color to green. Okay. Suppose I do y simple, then basically you can sketch an arrow going from down to top, right?
Mm-hmm.
And we're going to basically describe the first y it encounters and then the second y it encounters. Okay. How do we describe this y? What's the bottom y here? What's the bottom y? The function of bottom y. What's the function of the top y here? Suppose I'm trying to do y simple here. Okay. Any thoughts? Y simple requires us to, first of all, describe x between two constants, right? And describe y between two functions. It's easy to see that x would be easily bounded between -1 and 1, right? So left boundary and right boundary is easy to identify, which is -1 and 1. Now the question is the top function and the bottom function, right? Top function and bottom function. Now, because the region R is bounded by the circle, we know the circle would be x squared plus y squared equals 1. It's equation. Do you guys agree?
Yep.
Okay. So that tells us we can solve for y in terms of the x, right? So y squared would be 1 minus x squared, which means y would be plus minus root of 1 minus x squared. Will this be helpful?
Yes.
Yeah, so that tells you the top y would be the positive square root and the bottom y would be the negative square root. So if you write it out, you should have this root of 1 minus x squared as the upper bound, right? Upper bound, this is the top function it encounters. The bottom function it encounters will be the negative square root. So that means, yes, we can express this region R by using y simple expressions, but it looks pretty complicated, right? Especially the boundaries of y. So if you put this into the double integration, we will have to say this is integral from -1 to 1, and then from negative root of 1 minus x squared to positive 1 minus x squared. And then this whole integrand, once again, it's pretty complicated. And then following last principle, dA here would convert to dy because this y matches these two bonds, and then dx will be in the outside. So yes, you can do your v in this double integral in terms of x and y by using x, y coordinates, but apparently this is very complicated, right? You can try to attempt to find its antiderivative and evaluate those two, but it's gonna be take a long time. All right. But fortunately, instead of using x and y Cartesian coordinates, we can actually try to think of using polar coordinates, and that can dramatically decrease decrease the difficulty of this double integration. So we'll come back to this question in a few minutes once we introduce the double integration in polar coordinates. Okay, so keep this problem in mind. We'll come back to it. So before we talk about the double integration, we can see that the difficulty basically comes from describing this region of integration, right? The region of integration, if you use x and y, it's very complicated, including these square roots. So let's take a look at the integration region in polar coordinates. So this polar region can be simply classified as two types. One is called rectangular, one is non-rectangular, kind of similar to Cartesian. Rectangle, Cartesian region, and non-rectangular Cartesian region. For the polar rectangle region, it's also called polar sector. Okay, polar sector. So let's recall the rectangular region in Cartesian coordinates. In Cartesian coordinates, we're using x and y. And when it comes to rectangular region, we know basically it's talking about here x, so y, and it's rectangular region, right? So it's pretty straightforward. So basically, your x would be bounded by two constants, and y would be bounded by two constants, c and d. So here, x would be between constants a and b, and y would be bounded by two constants as well. You guys recall this?
Yes.
So this is the rectangular region in Cartesian coordinates, right? Similarly, polar coordinates has also a type of rectangular, even though it doesn't look exactly like a rectangle, but it uses the same idea of bounded by constants. Polar coordinates has two coordinates, r and theta. So we should have r, the radius, bounded by two constants, suppose radius 1 and radius 2. And the angle theta should be bounded by two constants as well. Suppose theta 1, theta 2, or you can call alpha beta. Okay. Suppose it's angle alpha and angle beta. Is that good?
Yes.
Okay, so let's try to see if you sketch it, what would that look like? Okay. So this is gonna be the polar axis, right? Polar axis. And then the radius is between R1. First of all, we can look at the theta. Theta is between alpha and beta. Now suppose this is my alpha, and here's my beta. So it'll be bounded between these two angles, right?
Mm-hmm.
And the radius would be bounded between radius 1, R1, okay, suppose I have an R1, radius R1, and then R2 will be its upper bound. Okay, let me extend this a little bit. R2. Is that good?
Yep.
With this in mind, can you sort of shade your region R here? Do you see the region that's bounded by this?
Yep.
Okay, so it should be between R and beta, alpha and beta, between R1 and R2. Therefore, it's going to be this region, right?
Mm-hmm.
So this the region R is the rectangular region in polar coordinates. This is also called polar sector. Okay, polar sector. So it's kind of like a fan, right? Part of the fan. Okay, fan shaped. Okay, polar sector. So the polar sector is the rectangular region in polar system. Let's look at a few examples. So example 1, use polar coordinates to describe a region here. Okay, there are two questions, A and B. In each question, there's a region R here, R. Let's first look at question A. Okay, question A, does that look like a polar sector?
Yes.
Okay, good. So this is a polar sector, which is rectangular in polar, right? And then let's just talk about R and theta. What are their bounds? First of all, for this region R, where does the radius start?
0.
Yeah, it starts from here, point, right? So 0, and ends at
2.
2. So R is between 0 and 2, pretty easy. What about the angle theta?
0 and 90 degrees.
So start from here, which is 0, and ends at here. We're gonna use radian. Okay, we're gonna use a radian measure. So this will be pi over 2. So we're gonna say theta is between 0 and pi over 2. Good.
Mm-hmm.
And the radius goes from 0 into here, which is 2, right? All right, what about second question here? Second question, it looks like fan, 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 fan. So it's like combination of 4 fans, right?
Mm-hmm.
It's, again, polar sector. Let's describe its radius and describe its theta. Okay, you guys, go ahead and figure it out, and I'll be back just in a minute. Okay, so have you guys got your description here? What do we say about radius?
Radius would be between 1 and 3.
Okay, between 1 and 3. Good. So 1 and 3. What about angle theta?
0 and 2 pi.
Yeah, so it starts out here, right, which is 0. And then it apparently goes 1 round, which is a 1 complete revolution. So that's 2 pi. Okay. So that's how I describe these two polar sectors. So attach the solution here. Yeah, the first one, radius between 0 and 2, theta between 0 and pi over 2. Second one, radius between 1 and 3, and then theta between 0 and 2 pi. But no matter what, you can see all of these are bounded by constants. Radius is bounded by constants, and theta is bounded by constants. Okay. So let's look at a polar rectangular region, which is a polar sector in detail. Okay, we have said polar sectors basically have radius between constants and theta between constants. And this is a graph when you try to sketch it, right? Between theta 1, theta 2, between radius r1 and radius r2. Now, if you look at this graph, you can tell the angle in between here is delta theta, the change of angle theta, from theta 1 to theta 2. Does that make sense? This angle will be change of theta.
Yes.
Change of angle. And this length here, okay, this length here will be, this length here will be change of the radius. So we have delta theta and delta r. Both can be expressed by looking at the graph here. So yeah, I should come back to this just a minute. And that's actually a conclusion. So the next question is, if we try to look at the double integration of this, suppose I have a sector, right? Angle theta between alpha and beta, and radius between A and B. How do I do the double integration? Okay. So double integration of function f of x, y, dA over r. If you change to polar, I can express the x by using r cosine theta very easily. I can express the y by using r sine theta, okay, due to the transition. So the next question is, how do I express the dA, right? dA previously is either in dx dy or dy dx by using Cartesian. And now you have to transfer that into radius r and angle theta. So the conclusion I've attached here, dA is actually r dr d theta, but why, right? Why the dA is actually radius times dr times d theta. Okay, so we're going to explain this just in a minute by looking at the following graph. You guys, is that clear for you?
Yes.
Okay, so we're talking about how do you convert a double integral from Cartesian to a polar coordinate. So that requires us to look at these polar sector in detail. If you recall in Riemann sum, right, in Riemann sum, we need to first of all get a partition of the region. So that's what we do here in this graph. You can see that the big polar sector has been partitioned sort of evenly, okay, evenly by angle and evenly by the radius into those small regions, right? So each of these small sectors would be a region. It would be adding the sum for Riemann sum. Now suppose this is the cave, okay, cave subregion it has got to. So here is the cave subregion. Okay. This cave subregion, I can choose a representative point, which is this point. So it's RK, okay, using R and a theta, and star for show this is the one that representative. And in rectangular region, the coordinates will just be xk star and yk star. Is that good so far, guys?
Yes.
Okay. And therefore, this little part will just be the change of radius, and this angle here will just be change of theta. Okay. Now let's see, how do we evaluate the change of area? Because that's what you need in Riemann sum, right? Riemann sum. So change of the area, which is this part. So change of area, the conclusion is RK star times delta R delta theta, but here we can do a quick proof. How do you get this change of the area, which is the shaded area of the cave? Okay, so delta AK. Now, delta AK could be computed by the subtraction of two regions. Okay, let me do my color here. Okay, so do regions. So the big region here, it could be the area of this big sector, right? Part in blue. Subtract the small sector. Subtract, okay. Okay, subtract this area. Can you guys see that from the graph? So the area of the red could be the area of the blue subtract area of the orange, right?
Yes.
Okay. I'm going to call the area of the blue, which is the one, call it to be A1. Let me go back to here. So delta AK will be the area of the blue region minus area of the orange region. And both of those two regions are in this shape, right, in this shape. So for these kind of graph, how do we calculate its area? Do you guys recall? So this is radius, this is theta. What's the area of such region?
R times the radius times arc length.
Yeah, it's it's related to R times the radius of arc length, except for it's going to be 1/2 R squared times theta, okay, which is 1/2 R times the arc length. You can treat this as a sort of a triangle look, right?
Mm-hmm.
So I can use this formula to calculate the area of the blue region and use this formula to calculate the area of the orange region. The difference will be the area of the shaded region that we're interested in. So let's do the area of the blue. That's going to be 1/2 its radius. Its radius is going to be this big radius, right? Big radius, which is going to be delta R add RK star minus delta R over 2. So that's going to be RK star, you add these two, plus 1/2 delta R square times the angle, delta theta. Is that good?
Yes.
Subtract the area of the orange, which is the smaller region, right? Smaller region. So 1/2 its radius. So its radius has been shown here, which is RK star minus delta R over 2. It's very easy to derive this part. So RK star minus delta R over 2 square and times the angle delta theta. So that will give us the area of the shaded region that we're interested in knowing. Okay. And apparently if you do the subtraction, they both share 1/2 delta theta, 1/2 delta theta. So I can just pull out 1/2 delta theta and I can just do the subtraction of those two squares, right? So RK star plus delta R over 2 square minus RK star minus delta R over 2 square. Next, if you expand these two perfect squares, if you expand the square, if you expand this perfect square, the RK star square would be canceled out. And delta R over 2 squared will be canceled out. So these two will all be canceled out. The item that's left will be 2 times RK star times delta R over 2 minus, here will be negative, which is plus, RK star times delta R over 2. That's what's going to be left if you do a quick subtraction of these two squares. So we have 1/2 delta theta. And you guys can tell that 2 and 1/2 cancels out. 2 and 1/2 cancels out. So what's left will be RK star times delta R plus RK star times delta R, which is 2 RK star times delta R. Therefore, I have 2 and 1/2 got reduced. In the end, I just get RK star times delta R times delta theta. Is that good?
Yes.
Yeah, this requires a little bit algebra work, okay, of applying the area of sector of, circular sector 2 times and find the difference. But anyway, what we have got is the delta AK, the delta A would be R times delta R times delta theta. Okay. So later on, okay, so based on delta AK equals RK star times delta R times delta theta, later on, this would just get us dA, differential A will be R dr d theta. Okay?
Yep.
And that is how this dA converts to this R dr d theta. It goes back to this formula, okay? Suppose I have a double integral in Cartesian. Now I want to convert that to polar. I need to convert the x and y, and I need to convert the dA into R dr d theta. This is very important over here. I want to put a star signal over here. The reason is dA is not just only dr d theta, it is R times dr d theta, especially this R in front of this dr d theta. That's kind of rare, right? It's not just dx dy. Now it's R dr d theta. Is that good? And then the radius will be between A and B, and the theta will be between alpha and beta, matching the limits and your variable. Good so far?
Yes.
Okay, let me check. Oh, I don't see it. Good. All right, next let's look at, why it's not moving here. All right, so now let's go back to this question that we started with. Okay, you guys recall the solid? The solid previously we were, folks, can you see my screen?
Yes.
Okay, so we were looking at the volume, right? So we said volume will be double integral of A, of this dA, of the region R, and then Z1, Z top, minus D bottom, And previously, we're doing the top function, which is 2 minus root of x squared plus y squared. Subtract the bottom function here, x squared plus y squared, and dA. And now we're going to do from xy coordinate to polar coordinates. The reason is the region of R, so the region of R here, can be expressed very easily by using polar coordinates, right? How do we express this region R here? By using polar.
Using the boundaries.
Yeah, using the boundary. Let's look at the radius and theta. Let's describe it. So radius will be between
0 and 1.
0 and 1. Okay, so 0 and 1. Okay, angle theta would be between
0 and 2 pi.
from 0 to 2 pi. So 0 to 2 pi, right? So you see, this time it's very easy to describe the region R by using R and theta. Okay. So R is easy and dA would be easy, right? So dA would be R dr d theta. Okay. And let's see, how do we express x squared and y squared? Here we know x would be R cosine theta, y would be R sine theta. And what's more is we have x squared plus y squared will just be R squared. Oopsie. Right, do we have that, guys?
Yes.
Okay, so let's see. I'm going to convert everything from xy to r and theta. So first of all, let's change these integrands. So I have 2 minus square root of r squared, because x squared plus y squared is just r squared, minus x squared plus y squared, that's r squared, right? And dA would be r dr d theta. So first to go.
Yep.
And now let's match our radius as the inner limits. So radius is between 0 and 1. And angle theta as the outer limits will be from 0 to 2 pi, right?
Mm-hmm.
Okay, let me rewrite it. So it's 0 to 2 pi, 0 to 1, and 2 minus r squared, r dr d theta. Good so far?
Yes.
All right, look at this integrand. Let's compare this double integral with the one we had derived before. Let's compare that with this. Can you see once you change to polar coordinates, it's much, much easier, folks?
Mm-hmm.
Right? It's much, much easier, especially the limits of the integration. They're both by constants. Okay. All right, next we'll just go ahead and evaluate this. Right. Is there any trick we can do here? Take a look at this integrand. Okay, take a look at this integrand. Is this integrand separable? Is this a separable function? Folks, can I write this function as a function of r times a function of theta?
Oh, yeah.
Right? Okay, this is actually a separable function. For this particular integrand, okay, it's a separable function. So I can use the trick that we learned before, right? If this is a separable function and the limits are bounded by constants, then I can just separate this as a function of r and a function, integral of theta, okay? The product of two double integrals. So let's put the r's together. So r is from 0 to 1. 0 to 1. And then you have 2 minus r squared times r. right? That's the part about r's. And there's nothing here for theta, so it's just multiplied by 1 d theta, and theta goes from 0 to 2 pi, right? Okay, and then you'll just need to evaluate this, okay? I'm going to multiply the r inside, distribute it. So I have 2r minus r squared minus r cubed dr times 0 to 2 pi 1 d theta. And in the derivative, this will be r squared, this will be r cubed over 3, this will be r fourth over 4, and radius r goes from 0 to 1, times second, and the derivative will just be theta. Theta runs from 0 to 2 pi. Okay, next evaluation is pretty straightforward. So I just have 1 minus 1/3 minus 1/4 times 2 pi minus 0, which would just be 2 pi. So it'll be 12. And this will be 7 over 12, so 5 over 12 and times 2 pi. Therefore, eventually I have 5 pi over 6 as the volume of the solid. Any questions? Folks, do you guys have any questions?
No.
Okay, good. So this question, we've converted all the Cartesian xy to polar r and theta. And we notice that for this particular case, it happens to be a separable function. So the double integration can be done of separating the double integral to 2 single integrals, right? Okay. And the conversion from Cartesian to polar has dramatically decreases the difficulty of evaluating this double integral. And again, the reason is because our region is a polar sector. Okay, polar sector. Okay, so this is one question. Next, I would like you guys to take a look at this problem here. Let's suppose we want to evaluate a double polar integral. So let R be this annual, this annular region lying between the 2 circles. Evaluate this double integral of x squared plus y dA over region R. Okay, first of all, we can tell this is r squared equals 1. This is r squared equals 5, right? You guys okay? So as for this inner circle, we can tell the radius will be 1. So radius will be 1. This outer circle, radius is actually root of 5, right? Root of 5. So as for this sort of ring, this ring could be expressed by using this description. So radius would be between 1 and a root of 5. Angle theta goes from 0 to 2 pi. Okay, from 0 to 2 pi. And now let's put this into our double integration. So double integration of my region R. Okay. X squared plus y. Okay, so notice that the region R could be written as r dr d theta. And then my radius r would go from 1 to root of 5. Angle theta would go from 0 to 2 pi. What do we do with the integrand here? What do we do with the x squared plus y?
Replace it with cosine and sine.
Yep, so we're going to replace x by r cosine theta, so r cosine theta squared, and replace y by, sorry, there is a square here. Y would be r sine theta. Okay. All right, Now, we have 0 to 2 pi, 1 to root of 5, and next you need to distribute the r, right? Distribute the r, I have r cubed cosine theta squared plus r squared sine theta times dr d theta. Good so far?
Yep.
Now, this integrand here, unfortunately, is not separable. Can you guys tell that it's not separable?
Yes.
Because if you take out r squared, you would still have r times cosine theta squared, right? R cannot be separated with the theta. So it's not separable, which means we'll have to follow our routine method of calculating the stubble integral. So you gotta do inner integral first and the outer integral. Okay, just follow those two steps. Let's go ahead and work on those two steps. Okay, so here, the inner integral would be 1 root of 5 r cubed cosine theta squared plus r squared sine theta dr. Okay, so variable is r. Theta will just be coefficient, right? Cosine theta squared and sine theta will be just coefficient. So let's do antiderivative of r cubed would be r to the 4th over 4 cosine theta squared plus this r squared would be r cubed over 3 sine theta, and my radius r goes from 1 to root of 5. So radius 1 goes 1 to root of 5. Is that good, folks?
Yep.
Okay, and then let's plug root of 5 in for the radius. Okay, so we should have 1/4. We have root of 5 to the 4th power. Okay, so it's going to be 5 squared, right? It's going to be root of 5 squared and a square. So 5 squared, which is 25. 25 over 4 cosine theta squared plus 1/3. And I'm going to root of 3 cubed, root of 5 cubed. It'll be root of 5 squared times additional root of 5. So 5 root of 5. Sine theta. And subtract whatever you write for radius equals 1. So 1/4 cosine theta squared plus, I'm going to further subtract 1/3 sine theta. Is everything good?
Yep.
Let's see if we can first combine some of the like terms. So apparently we can try to combine the cosine theta term. Okay, so 25 over 4 and 1 over 4. Subtract those two, I get 24 over 4, which is 6 cosine theta squared, and plus 1/3, 5 root of 5 minus 1. 5 root of 5 minus 1 sine theta. Okay, so this finishes the inner integral, right? Inner integral. And we still have the outer integral from 1 to root of 5. Oh, sorry, from 0 to 2 pi, right? The outer integral, d theta. 0 to 2 pi d theta. And you put this part inside. So 6 cosine theta squared. And then plus 1/3, 5 root of 5 minus 1 sine theta d theta. Okay. How do you find the antiderivative for cosine theta squared? Any thoughts?
You could probably rewrite it. Or
Yes, you have to rewrite it in a double angle formula, right?
Mhm.
So cosine theta squared equals 1/2 1 plus cosine 2 theta, right? If you use the double angle formula. Therefore, integral of this cosine theta squared d theta will be integral of that, which will be integral of 1/2 plus 1/2 cosine 2 theta d theta. This will be 1/2 theta plus 1/2, and this will be sine 2 theta divided by 2, right?
Yep.
Okay, so we're going to apply that formula. So 6 times, 6 is the coefficient, integral of cosine theta squared. So we have 1/2 theta plus 1/4 sine 2 theta. That's the antiderivative of this cosine theta squared. The second part is pretty straightforward, right? So 1/3, 5 root of 5 minus 1. Antiderivative for sine theta would just be negative cosine theta, right? And then we're going to plug theta, 0, and 2 pi in. Okay, let's see what we get if you plug 2 pi in. So 2 pi, 2 pi, and 2 pi. So we should have 6 times 1/2 times 2 pi, which is pi, and plus sine times 4 pi, which is 0, right? So 0 plus 5 root of 5 minus 1 over 3. What's negative cosine 2 pi? Negative cosine 2
This
pi.
is -1.
Correct, -1. All right, so that's what you get when you plug 2 pi in. And next, let's plug 0 in. So 0 goes in. Okay. If 0 goes in, you may see that lots of zeros coming up, right? So we have 0 here, plus sine 0, again, that's going to be 0. Okay, and then we have, this part would be plus 5 root of 5 minus 1 over 3. Once 0 gets in, you get another -1. Right?
Yep.
Okay, so we can see that a lot of the items would be canceled out, like 5 root of 5 minus 1 over 3 times -1 would cancel out with this piece. And I have 6 pi minus 6 times 0. So towards the end, our conclusion will just be 6 pi, right?
Yep.
Yeah, because we have 6 pi minus 0. Okay. So this double integral turns out to be 6 pi by the conversion from Cartesian to polar. All right, so we have the solution over here, attached tiles again. Okay. All right, let's see how much time we have. Yeah, we still have time. Let me see. Yep. So next, we talk about polar rectangular. Next will be polar non-rectangular region, right? Non-rectangular, which is just the general polar region. Okay, general polar region. General polar region is the one that you see more often. Okay, it's kind of like the general Cartesian region that we see a lot of times. So let's recall the non-rectangular region in Cartesian that we talked about in last section. Okay. In Cartesian coordinates, we have non-rectangular region. Basically, they could be further classified as two groups. One is called X simple region, one is called Y simple region, right?
Yep.
So similarly, for the polar coordinates, you would have R simple region and theta simple region. Make sense, folks?
Yep.
Okay. For X simple region, we said X must be bounded by two functions, right? So function of Y, function of Y, and Y must be bounded by two constants, so C and D. The graph, if you look at it in Cartesian, for X simple region, basically Y has to be bounded by two constants, C and D. X needs to be bounded by two functions. So suppose this is one function, this is another function. This is going to be the X simple region, right?
Yep.
Okay, Y simple, let's recall what we talked about last time. So Y simple means Y needs to be bounded by two functions of X. So say fx gx, and X needs to be bounded by two constants, A and B. The graph looks like X bounded by two constants, so A, B, and Y would be bounded by two functions. One is lower bound, one is upper bound, right? Like this. These are two straight lines. So this is going to be the Y simple region. Okay, did we talk about one way to identify whether it's X simple, Y simple very quickly? By drawing the arrow, right? You guys recall, recall the arrow drawing? We said if you can draw an arrow for X simple region, then you pretty much draw an arrow vertically in the following the X direction. For Y simple region, you can draw an arrow going through this region vertically. Oh, sorry, the first one is horizontally, the second one is vertically. So X simple and Y simple. So we can use the similar idea for R simple and theta simple. Okay, theta simple. For R simple, the R must be bounded by two functions of theta. So say f of theta, g of theta. And theta needs to be bounded by two constants, right? So let's say alpha and beta. Make sense?
Yep.
Let's see, what would the graph look like? Okay, the graph would look like, first of all, let's do the polar axis. Theta has to be bounded by two constants. So you should have theta equals alpha, theta equals beta as these two straight lines because these are constants, right? And then my radius would be bounded by two functions. They're no longer constant radius. So I may have first radius looking like this, and second radius may look like this. Okay, so this is f theta, here's r equals f theta, here is r equals g of theta. Make sense?
Yep.
And then you would have the region that's bounded in between, right, bounded in between. In this case, how would we like to sketch the arrow, folks?
For the R simple region?
For our simple region, how would you like to sketch the arrow, like X and Y that we did before?
From the origin?
From the origin, and let's just sketch an arrow going this way. Make sense?
Yep.
Then you can tell that it intersects the first graph, which is r equals f of theta, and the second graph, r equals g of theta. So this is our simple region. Lastly, let's finish the theta simple region. I'm sure that you guys probably can write down the basic description for theta simple region. First of all, theta simple, theta would be bounded by two functions of radius, so f of r, g of r. And the radius will need to be bounded by two constants, right? So I'm going to say r1, r2, radius. And let's sketch its graph this time. Okay, so with the radius being bounded by two constants, I have r1 and r2 as two constants, right? Your radius will be bounded in between those two. Is that all right, folks?
Yep.
And then we should look at the theta, okay, which is for angle. If angle equals to a constant, then it's going to be a straight line, but this time angle will be bounded by a function. So I'm just, in general, just draw a curve. This will be theta equals to f of r. And secondly, I have theta equals g of r. I'm going to put another one, so theta equals g of r, right? And this will be the region bounded in between. Okay, how do we sketch the arrow this time? Which arrow you can draw to intersect these two thetas? I'm going to draw the arrow this time, kind of weird. Okay. It's not a straight arrow. It's going to be following this circle, right?
Yep.
Going this way. Okay. Previously it's for r symbol, so in the r direction, radius direction, this time it will be in the theta direction because theta goes circularly. Okay. So theta direction and intersects, first of all, theta equals to f of r. Secondly, theta equals to g of r. So that's going to be the theta symbol region. Okay. I hope you guys are still fine. Are you guys following me?
Yes.
Okay, great. So next, let's try to look at a few examples and to see whether they are r symbol or theta symbol. Okay. Oh, yeah, this is a graph sort of recaps what we just discussed. Okay, now let's look at example 4 here. Example 4, we have a circle here which can be expressed by r equals 2. We have another circle whose center is on the x-axis, which is expressed by r equals 4 cosine theta. And there is a shaded area which is the intersection, which is the part that's outside of the intersection area in the second circle. Would this shaded area be r symbol or theta symbol? Shaded region R.
R simple.
Yeah, this might be helpful with these information printed on the graph already. So it looks like the theta needs to be bounded by these two straight lines, right? Theta will be bounded by negative pi over 3 and pi over 3. And for the radius, first of all, it intersects this curve, which is 2. Secondly, it intersects this curve, which is from r equals 4 cosine theta. So if I write down my region R, okay, I can express this region R with the description of radius and a theta. And angle theta has to be from negative pi over 3 to positive pi over 3. And the radius would start from this radius, which is r equals to 2, and ends at this radius, which is 4 cosine theta. Therefore, this is a r symbol region, right? You can also tell that I've already sketched this arrow going from the r direction, right? R direction. So it's an easy way for to tell that's r symbol region by looking at the arrow as well. Questions?
No.
Okay. So in fact, our simple region is pretty common. Okay, compared to theta simple region. Okay. So if it happens to be our simple region, okay, suppose that's our simple region. Our simple region. How do we do the double integration in our simple region? So pretty much the same. If the radius r is between two functions and theta is between two constants, we put the constants in the outer layer, so alpha beta, right? Alpha beta. And we put the functions in the inner layer. And then you replace the x and y by r cosine theta and r sine theta. And you still follow with the r dr, because r would match this h theta, g theta, and theta will be alpha and beta. Okay, guys, next, I'll give you guys a few minutes to think about example 5, and I'll be right back and talk about how do we set this up. Okay. So use integration in polar coordinates to evaluate this double integration, okay, double integral. Okay, any thoughts? First of all, once we convert everything to polar, we can see x squared plus y squared will just be r squared. So the integrand will just be sine r squared, right?
Yep.
Now the question is, how do we convert this this region R? Okay. So that, first of all, we need to know what is the region R, what does it look like? Okay, so let's first look at this region R in XY, in Cartesian. So region R, if we describe that in Cartesian, we should have y goes from 0 to 1, and x goes from 0 to root of 1 minus y squared, right? Looks like this is an x simple region. Y is easy to sketch, just between two horizontal lines, and here x is between 0 and a root of 1 minus y squared. So this is, what is this part? What's the graph of this part?
It would just be, wait, never mind.
Let's just look at x equals to 1, root of 1 minus y squared, 1 minus y squared. Can we simplify this further?
Wouldn't it just be half of a circle? Or
Correct, yeah, it's really just a circle, good. So we should have x squared equals to
1 minus y squared?
Yes. And you should have x squared plus y squared equals 1, right? This is a circle. Actually, it's a unit circle because the radius is 1. So the second part actually comes from a unit circle. And what's more importantly is x is a positive part of the square root. So x needs to be positive, right? Okay. And let's try to sketch it. Let's sketch this region to take a closer look. Okay. I'm going to first, remember this is still in Cartesian, so x, y. Now my y is between 0 and 1, 0 and 1 here, right, 0 and 1. My x starts from 0, which is going to be this line, ends at this root of 1 minus y squared, which we know is from unit circle. Right?
Yep.
Okay, do you see the region R? Which one is that region R that you can highlight, sort of shade it? So it needs to be between 0 and a 1 for y. X needs to be from 0 and to the circle. So apparently it's going to be this a quarter of the circle, right?
Mm-hmm.
Okay, then how do we convert this region R by using polar? Next question is we need to convert that from Cartesian to polar.
Just change the boundary points.
Yeah, change the boundary, and let's describe that by using R and a theta. So if we describe that in polar, we should say radius would go from, radius is between, what's the radius? Between 0 and 1, right?
Mm-hmm.
And theta here, angle theta here, will be between 0 and what? What's this is the beginning theta, right? And this is the ending theta. Isn't that pi over 2?
Yep.
Okay, so this happens to be still a rectangular polar sector, right? It's a polar sector. All right, but what we see here is you need to look at the region R originally in Cartesian and convert that to polar. All right, now let's just rewrite this double integral. So double integral now would be integral of R sine R squared, and dx dy would convert to R dr d theta, right? Dx dy now is R dr d theta. Let me just finish that up, and then we should be done real quick here. And let's just put the limits here. The radius is between 0 and 1. Angle theta is between 0 and a pi over 2. All right?
Yep.
All right, we're out of time for 1 minute, so I'm just gonna stop right here, guys. And we're gonna continue this topic next time. It's gonna be next Monday, because we don't meet on Friday. Okay, you guys have a wonderful break. Although I know you guys have been at home like a break for quite a while, right? Okay, yeah. Just let me know if you have any questions. Okay.
I have questions.
Yeah, is it Donovan?
Jonathan.
Jonathan, sure, Jonathan.
It's about the test.
Mm-hmm.
It says you have to have 2 on each page. What if we have 3?
It'd be 1 or 2. So ideally, I would like you guys to separate your solutions so I can see them very clearly. It's okay if you just have to put 3 on it.
Okay.
Yeah. Mm-hmm. Do you have other questions, Jonathan?
Not really.
Okay, great. Okay, so folks, I will assign a few questions on the microcourses for exercise of this polar coordinates, and then we'll come back on Monday, okay, to talk about any problems you may have. All right, and I'm gonna see you guys next Monday then. Okay.